Hello, everyone. Let's now turn our attention to the structure of demographic rates and how we measure population exposure over time through something called person years. If you've ever read statistics like birth rate or mortality rate, you've encountered these ideas already, even if you didn't know how they were calculated. So let's break it down together. Let's begin with a simple question. How does a population change in size over time? There are four fundamental flows: births, deaths, in-migration, out-migration. These flows, when added or subtracted, determine whether a population grows, shrinks, or remains stable. Now, here's something interesting. Most of these events happen to individual people. A person dies, a couple gives birth, someone moves into or out of the country. But when we analyze population data, we're not just counting events, we're relating them to the population that could experience them. The demographic rate helps us compare events like births and deaths relative to the size of the population. This is essential because a large population will obviously have more events just by size alone. The demographic rate is obtained by dividing the number of events by the person years of exposure. Let's pause here. That denominator, person years of exposure, is what gives the rate real meaning. It's not just about how many people there are, but how long they were at risk of the event. Let me give you an analogy. Imagine you're analyzing car accidents. You don't just want to know how many crashes occurred. You want to know how often crashes occurred per 100,000 miles driven. Why? Because driving more miles means more exposure to the risk. In the same way, in demography, we want to measure how many events, say births or deaths, happen per unit of time people are at risk. So, what are person years? A person year is one person living for 1 year. If one person lives for 10 years, that's 10 person years. If 10 people each live for 1 year, that's also 10 person years. Now, suppose someone lives only for 6 months in the population during our study period, that's 0.5 person years. We total up all these contributions to build the denominator of our rate. We can visualize this using lifelines, a tool demographers use to track individuals from birth to death and mark the events that happen in between. Imagine a horizontal line from birth, point A, to death, point B. If someone gives birth at age 25, we mark that event on the line. These diagrams help us understand when people are exposed to the risk of different events. For example, if we're studying fertility, we only consider the lifelines of women of childbearing age because others are not exposed to the risk of childbirth. Let's say we want to calculate the fertility rate for women aged 20-35 over a 5 year period. Here's what we do: count all births from women in that age group. Calculate how many person years those women contributed during the 5 years. Divide births by person years to get the rate. Fertility rate, number of births, person years of exposure. Simple, right? This allows us to compare different groups, time periods, or countries, even if their population sizes are different. Now, let's talk about period rates. A period rate focuses on a specific time window, like a calendar year, and counts all the events, births, deaths, etc., that occurred in that time, all the person years contributed by people alive during that time. Even if someone lived only part of the year, we still count their partial contribution. If someone lived from April 1st to October 1st, that's 6 months or 0.5 person years. Let's walk through an example. Imagine a small population with 7 people in 1981. 4 people were alive the whole year. 4 person years. One person was born in April and died in October. 0.5 person years. Two others were present for 3 months each. 0.25 person years each. Total person years: 4 plus 0.5 plus 0.25 plus 0.25, 5 person years. Let's calculate the death rate using the concept of person years. In our example, the total number of person years in 1981 was 5. Now, we're told that 2 people died during that year. To find the death rate per person year, we divide the number of deaths by the total person years. Death rate, sin of 2 divided by 5, which equals 0.4 deaths per person year. This means that, on average, for every year of exposure by one person, there were 0.4 deaths in the population. But often, we express death rates in a standardized way, per 1,000 person years, so they're easier to compare across populations. So we take that 0.4 and multiply it by 1,000. 0.4x 1,000 or 400 deaths per 1,000 person years. In summary, this population experienced a death rate of 0.4 deaths per person year, or 400 deaths per 1,000 person years in 1981. This helps us compare mortality risk across different population sizes and time periods in a consistent, meaningful way. Another way to calculate person years is to estimate the average number of people alive during the period and multiply by the length of the time window. We can use quarterly or monthly population counts. Say, average population